Hey everybody, I hope you all had a safe break. So what the TAs have decided to do is we are all going to be taking turns and recording some videos for you since you obviously can't come anymore to the PARTE sessions. So what we're going to do is we're going to walk through all of the PARTE packets for the next coming weeks and go through the answers to those. So if you are interested in doing the PARTE worksheets, they'll be uploaded on Blackboard and you can do them the same way that you've been doing them before, but on your own, and then you can come watch the video to see how to do the answers to these questions. So this week 9, we're going to be focusing on Lewis structures. So first I'm going to walk through a way to draw each of the Lewis structures. So just to walk through the process here, first what you want to do is you want to count the valence electrons. So the easiest way to show this is I will do an example problem and show you how this works. So the first problem says to do carbon dioxide. So the valence electrons for carbon dioxide are going to be carbon and then 2 times oxygen. So carbon is going to have 4 valence electrons, and then oxygen is going to have 6 each based on where it is in the periodic table. And based on that, we have 4 plus 6 plus 6, which is equal to 16 valence electrons. So next what we'll do is we'll draw the molecule with single bonds. So in order to do that, we need to determine which one is going to be our central atom. So with this one, it's pretty easy because you can see that you have a carbon and 2 oxygens. And how I like to determine it is you kind of think of the atom that is the most hungry for electrons, or it's the least electronegative, and it wants more electrons. So oxygen wants 2 more to complete its full octet, and carbon wants 4 more. So carbon wants more of them. It wants to share more electrons. It wants to have more bonds. So I guess saying hungry for it is not really right because that would imply it's more electronegative, and we want something that's less electronegative. So carbon is less than oxygen based on our periodic trends, and then also carbon has 4 valence electrons and oxygen has 6. So we're choosing carbon as our central, and then we'll draw single bonds to put the 2 O's next to the carbon. So now we will add the remaining lone pairs of electrons. So we have 16 electrons to distribute. So we have 1, 2, 3, 4 in each of the single bonds. And then we'll say 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, now let's check to see if all of our atoms have the right number of electrons. So oxygen will count everything, all of its lone pairs and all of its bonds. So we'll do 1, 2, 3, 4, 5, 6 in lone pairs, and then 2 for this single bond. So oxygen is 8, so it's happy. This oxygen is the same thing, 1, 2, 3, 4, 5, 6, 7, 8, so it's also happy. But this carbon in the middle here, 1, 2, 3, 4, it only has 4. So what that means is that we need to form another bond with carbon. So since both of these oxygens have enough electrons, they can share their electrons. This carbon is lacking in 4 electrons. So what we can do is we can make more bonds with carbon. And we'll redraw this as carbon with double bond to oxygen, double bond to oxygen. And we put these electrons into this bond and these electrons into this bond. So now we just have 2 lone pairs and 2 lone pairs. So that makes 1, 2, 3, 4, 5, 6, 7, 8 on this oxygen, 1, 2, 3, 4, 5, 6, 7, 8 on this carbon, and 1, 2, 3, 4, 5, 6, 7, 8 on this oxygen. So this one's good. So that's what this step is. Pi bonds, those are going to be double and triple bonds. So that step was just taking some lone pairs and giving it to atoms that are lacking in electrons. And then finally we'll determine formal charges, because sometimes you might come up with more than one Lewis structure, so you need to see which one is correct. So the way that you do formal charges is you count up the number of electrons that are kind of associated with each atom. So instead of saying that a single bond is worth 2, this time we're saying that single bonds are worth 1, because we're kind of saying, like, if we were to split right here, one of the electrons would be held by carbon and one would be held by oxygen with each bond. So if we count for formal charges, we would say 1, 2, 3, 4 for lone pairs, and then we have 2 single bonds, 2 bonds, and so we would say 2 electrons. So this oxygen would have 6. And what we need to do here is we need to say that number 6 minus the number of valence electrons that it has, and that's going to equal 0. And that means that this oxygen has 0 formal charge. So let's go to carbon now. This carbon has 1, 2, 3, 4 bonds, so it's going to have 4. And then the number of valence electrons that it has is also going to be 4, because based on the periodic table, that's how many valence electrons we have. So 4 minus 4 is equal to 0. So the carbon is also 0 formal charge. And then this oxygen is identical to the other one, with 1, 2, 3, 4 lone pairs, and then 1, 2 for the single bonds. So that one is also going to be 0. So overall, this compound has 0 charges. So just some tips and tricks for all of the rest of these problems. The most electron poor atom is going to be your center one. So kind of like we went through here, the carbon only had 4 valence electrons. It wants 4 more. So that means that it's going to be the center. And then you might want to memorize atoms' tendencies to form multiple bonds. So based on, you're going to become really, really familiar with carbon and oxygen, and probably nitrogen as well. Carbon likes to form 4 bonds. That's just a pretty hard and solid rule. Carbon will pretty much always form 4 because it has 4 valence electrons. Oxygen will almost always form 2. Oxygen is a little bit more likely to have charges on it, but that's just something that you can memorize. So we'll go to the first problem. So on purpose, kind of, I already walked through this one. So I will just literally copy this onto this slide, because I already showed you guys how to do that. So we had carbon with double bond oxygen, and then we had these lone pairs like this. So looking at our answer choices, we see that the correct answer here is going to be A. So then let's go to the next one. So this one requires us to draw a Lewis structure for O2. So let's go through. Count the valence electrons is our first step. So oxygen has 6. And we have 2 of them. So we have a total of 12. And then we'll draw our molecule with single bonds. So it's going to be O2. So just oxygen, oxygen. We have 1, 2 right here. So now we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now let's count up our electrons to see which atom's lacking. So this oxygen we'll start with. We have 1, 2, 3, 4, 5, 6, 7, 8. And then this one has 1, 2, 3, 4, 5, 6. So this oxygen needs 2 more. This one can share it. So let's make a double bond here. And then now let's look at the formal charges. First of all, we'll check really quick if both of these have 8. So 1, 2, 3, 4 from the double bond. 5, 6, 7, 8. So this oxygen's good. 1, 2, 3, 4, 5, 6, 7, 8. This one's also good. And then we'll look at the formal charges. So this guy has 6 valence electrons, and then it's 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0, and the other oxygen is the same. So both of these have a net charge of 0. So based on our Lewis structure, we can see that the correct answer is also A, because we have a double bond between O2. All right, on to number 3. So this one asks about SEF4. So you might not know off the top of your head what Se is. Selenium, on my periodic table here, you can see that selenium is in the same family as oxygen and sulfur. So it has 6. And then fluorine up here is a halogen and has 7 valence electrons. So we can start here by counting our valence electrons. And Se has 6, and then F has 7 times 4, so that's going to equal 28 plus 6, so we have 34 valence electrons. So now let's draw our Lewis structure. So the most electronegative, or the least electronegative, or the most electron poor atom here is going to be selenium over fluorine, because we have 6 instead of 7 valence electrons. So we'll draw it in the middle, and then we'll put our 4 fluorines on the outside. So now we can start putting on our extra electrons. So we have 34. 1, 2, 3, 4, 5, 6, 7, 8 are already here. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So all of these fluorines now have full octets. So the only place that we can put our extra is on the selenium here. So this might seem kind of strange, because if you notice here, selenium now has more electrons associated with it than what we would think, because it has that full shell. But selenium is a little special. We can put more electrons on it than 8 because of where it is in the periodic table. So you can see that it has a 4p orbital and it also has a 3d. So because it's a larger atom down in the 3rd or 4th row, we're allowed to put more electrons on it. And that's because we kind of would have to put them on the selenium. We can't make double bonds with the fluorine, because the fluorine definitely can't have more than 8. So if we look at our answer choices here, the question asks, what is the total number of electron pairs in the valence shell of selenium? So we have 4 single bonds and then 1 lone pair. So that's a total of 5 pairs, and 4 of them we would consider bonding pairs, and then 1 is a lone pair, so it's non-bonding. So the answer here would be B. All right, so on to number 4. So this one asked about CS2. So carbon, we know carbon, but you might not be familiar with S or sulfur. It's going to be below oxygen. So it's similar to oxygen where we have 6 valence electrons. So carbon is going to have 4 valence electrons. And then S is going to be 6 valence electrons. So that means that we have a total of 16 because we have 2 sulfurs. So I'm going to cheat a little bit because if you remember back to our first one, our first example, we did CO2, and now we're doing CS2, which these are essentially going to be, they're going to look like the same Lewis structure because sulfur has the same number of valence electrons as oxygen. So just for time's sake of this video, I am just going to copy the Lewis structure, but with S's instead. Hopefully that makes sense why we could do that. It's because S is very similar to oxygen because they're in the same family. That's why we can do that in this Lewis structure. So the number of bonding electron pairs in the best Lewis structure is going to be 4 here because, see, we have 4 bonds. So the number of bonding electron pairs literally just refers to how many bonds are there in this atom, or in this molecule, excuse me. All right. On to number 5. So, which of the following is the correct Lewis dot structure for OF2? So, OF2 is going to have oxygen, which is 6 valence electrons, and F, which is 7 times 2. So that's equal to 20 valence electrons. And based on up here, we know that our only options are going to be O with the F's on the sides. And now we just need to add up our electrons to put on here. So it's usually a safe bet to go for the fluorines first, or the terminal atoms first. So let's see how many we have so far. So 20, 1, 2, 3, 4 from the single bonds, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and then 17, 18, 19, 20. So that Lewis structure right there looks all right to me. I don't think we need to make any double bonds or anything because we have 1, 2, 3, 4, 5, 6, 7, 8 on the fluorine, 1, 2, 3, 4, 5, 6, 7, 8 on the oxygen, 1, 2, 3, 4, 5, 6, 7, 8 on the fluorine. So the answer here is going to be B. All right, on to number 6. So now we are going to look at SiH4. So something that you can memorize here, hydrogen is always going to be terminal. Hydrogen forms 1 bond, and that's it. Because hydrogen, to have a full octet, only does 2 electrons, so it just makes a single bond. So silicon is similar to carbon, because it's in the same period, or excuse me, it's in the same family. So it's just one right below carbon. So silicon has 4, and then H has 1 times 4. So that means that we have 8 total. So silicon's going to be our central one. And then we'll put our 4 H's on the outside. So if we count up our electrons, that's 1, 2, 3, 4, 5, 6, 7, 8. So this is the complete Lewis structure. We don't need to keep going because we put all our electrons on there. And if we check, all the hydrogens have 2 electrons associated with it, so they're happy. And then the silicon has 1, 2, 3, 4, 5, 6, 7, 8. So this is good. So then if you go through your answer choices, the answer here would be E, because there are 4 single bonds to silicon. All right, so the next one is to draw the best Lewis structure for SOCl2. So this says in the problem, S is the central atom, because we might wonder, like, oh, S has 6 valence electrons, and O has 6 valence electrons as well. So which one do we pick? Well, it tells us right here that S is the central one. We also know that, well, I won't get into that. And then chlorine has 7 valence electrons. So if we do our typical S in the middle, and then oxygen and chlorines on the outside, and then all of this added up is going to be 26. So we have 1, 2, 3, 4, 5, 6 from the single bonds, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and then we got to put the last ones, 25 and 26, right there on silver. So now what we need to do is look at our charges here. So if we look, we can see that this sulfur does have 8 electrons with it. But if we look at formal charges, we can see that the lone pairs here would be 1, 2, and then with the single bonds, we see that we can only count 1 per each single bond. So this has 1, 2, 3, 4, 5 electrons associated with it. So if it normally has 6 valence electrons, minus 5 electrons that we found it has, that's 1. So this guy has a +1 charge. And then if we look at the oxygen, it has 1, 2, 3, 4, 5, 6, 7. So it normally has 6, and then we subtract that number that we counted, so it's -1. So the oxygen has a negative charge. So if there's some way that we can move the electrons around, that these would be a little happier, that's better for us, because we want to get rid of formal charges to have the best possible thing. So the best structure, what we would do is we would make this oxygen form a double bond, because like I said before, oxygen really likes to have 2 bonds. It's pretty stable that way. So what we're going to do here is just draw it down here. We have a double bond with oxygen. And nothing has changed down here, but now we have this lone pair here. And then we have this oxygen is now happy because we now have 1, 2, 3, 4, 5, 6 associated with it, electrons. so 0 formal charge. The sulfur has 1, 2, 3, 4, 5, 6, so it also has 0 formal charge. So you might be like, wait a second, this is confusing. Why does this sulfur have more on its valence shell? Well, the reason that we can do that is if you look at where sulfur is on the periodic table, if it's in the 3rd row, then you're allowed to give it a few more valence electrons in order to satisfy formal charges. And everything else is happy because everything else has 8. So that is why this is the best structure for SOCl2, thionyl chloride. So now we'll do a little bit of an easier one. Oh, just kidding. We have number 8 to do. So we need to draw the best Lewis structure for CH3 and H2. So now we have 3 atoms. Exciting. So we have carbon, which has 4, nitrogen, which has 5, and then we have a total of 5 H's. And I can show you why they separated this. They actually made things a little easier on you because they kind of showed you where the H's are based on how this is written out. So we have 5 H's. So that's going to equal 14 valence electrons. So we know that because carbon wants 4 more electrons, that's more than any of the others. So it's going to be the central. And then right away you can tell there's more than 4 atoms here, so we can't just like put them all around the carbon. So we can go to our next largest one. And then something special from this Lewis structure that you can tell is they've split it into H3 and then N and then H2. So what that kind of makes it seem like is that they want you to kind of split up this atom into like thinking of it as CH3 and then bonded to NH2. So if we put the 3 H's on the carbon, we can say that the other 2 go on the hydrogen. So let's count up our electrons now. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 2 more. So it might not be immediately obvious where to put your electrons, but if you look, carbon already has 4 electrons in its valence shell now because we have 4 bonds, each with 2 electrons. So 4 times 2 is 8. Nitrogen, however, only has 6 because we just have 3 bonds with it. So we'll stick the lone pair on nitrogen. So this is going to be the best for CH3NH. Okay, now a much easier one. So this one is CCl4. Carbon is 4. Cl is 7 times 4. So the toughest part of this problem is the math, at least if you're doing it in your head like I am. So we have 32 valence electrons. The carbon goes in the middle because it has 4 valence electrons instead of 7. So it wants 4 more. The chlorines only want 1. So we'll put the chlorines around, and then we'll start putting on electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And that's all the electrons that we need. And each of these, if you'll notice, has a complete set of 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that's for the carbon. And then each of these has 3 lone pairs and 1 single bond. So it looks like we are good. We don't need to make any double bonds. But then let's look at formal charges. So I will just look at carbon and chlorine for this. because all of the chlorines are the same. So I'm just going to look at one of the chlorines. So the carbon has 1, 2, 3, 4, well, sorry, you just need to count one bond, one per bond. So 1, 2, 3, 4, and it has 4 valence electrons, so that's 0. So no formal charge on the carbon. And then chlorine has 7 valence electrons, and we count 1, 2, 3, 4, 5, 6, 7. So we have a formal charge of 0 on both. So this is a good structure, and that's the answer for this one. Okay, one more draw the best Lewis structure for hydrazine. So this one, they kind of help you out because they draw NH2, NH2, because they're kind of like splitting up the molecule for you to give you a hint of how to draw it. But first, let's look at nitrogen, which has 5, and hydrogen, which has 1 valence electrons. And then we've got so 10 plus 4, so we have 14. We have 14 valence electrons to work with. So we know that nitrogen is going to go in the middle. But what we don't know beyond that is where everything else goes. So the way that they've split this up is kind of saying there's an NH2 on one side and an NH2 on the other side. And we know that hydrogens have to be terminal, which means they have to be on the ends of the molecules because they can only form one bond. So it's kind of like it's like the caboose at the end of the train. There's like no connector for the next train car, so it has to be the end. So the nitrogen has to be bonded to another nitrogen to have the rest of the molecule, but the hydrogens automatically end the molecule. So I'm doing 2 hydrogens on each because they have a split NH2, NH2. So moving on to how many electrons we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 4 more to put. So I'll just be fair and put 2 on this nitrogen and 2 on this nitrogen. So now we have 1, 2, 3 bonds plus a lone pair on this nitrogen, so it's happy. And then the same thing with this guy. So we don't need to make any pi bonds. So now let's determine the formal charges. So nitrogen has 5, and we'll count how many electrons it has. So we have 1, 2 here, and then we count each of the single bonds once. So 3, 4, 5. So this guy is happy, and then this nitrogen is also the same. And then this hydrogen, it can only have a formal charge of 1 because it only has 1 bond and it doesn't have any lone pairs. So this is the best structure for hydrazine. Okay. Oh, looks like I lied. There is one more of the draw the best Lewis structure. So this is for HCN, and it tells you that carbon is the central atom, but we would know that because carbon has 4 and nitrogen has 5 valence electrons, so carbon wants more than nitrogen does. So adding up these, we have 10 total valence electrons. So if we put carbon in the middle, then we need to start putting on more electrons because we just have 1, 2, 3, 4. So we'll say 5, 6, 7, 8, 9, 10. All right, so we know that this is wrong because this nitrogen hardly has any electrons on it. So this hydrogen is good because it only wants 2. So it's single bond and it's happy. Carbon has 1, 2, 3, 4, 5, 6, 7, 8. So carbon's also good, but we'll see that that's going to have a crazy formal charge on it because it only likes to have 4 electrons associated with it, with like usually 4 bonds on it. It doesn't typically have lone pairs. And then this nitrogen, we only have 4. So what we're going to do is we're going to make these lone pairs into multiple bonds so that we're sharing with the nitrogen. So we will draw this again, and then we will do a triple bond and keep this lone pair here. So now if we count up our octets, so hydrogen still has 2, still good. Carbon has 1, 2, 3, 4, 5, 6, 7, 8, so it's good. And then nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen is good. So now let's look at formal charges. So hydrogen has 2 and hydrogen has 1, and then it only has 1 electron with it from this side of the bond. So that one's happy. Carbon, we count 1 for each bond, and it has 4 valence minus 4 electrons is 0. And then this nitrogen has normally 5 valence electrons, and then we count 1, 2, 3, 4, 5. So formal charge is 0. All right. So this one, we get to determine which of the following Lewis structures is incorrect. So what we need to do here is we will determine which one is wrong based on the number of total electrons. That seems to be the pretty much easiest way to do that. So it's a little tedious, but it'll get you the right answer. So for this first one, A, we have nitrogen and we have 3 oxygens. So we'll have 5 valence electrons plus 3 times 6, which is 18 plus 5, so we should have 23. So let's count up to see, oh, and also we have an additional electron here because this entire compound is charged with a negative 1. And what that means is that we have an additional electron. So kind of like if we ionize something and it has an additional electron, it's like that. So we'll actually have 24. So let's count. So if we count all of our bonds first, 2, 4, 6, 8, and then we'll count the lone pairs. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So this one is good. So next we'll look at B. So we have chlorine, which has 7. We have nitrogen, which has 5 valence electrons, and oxygen, which has 6 valence electrons. So we should have a total of 18 valence electrons. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, that's not quite enough because we need to have 2 more. So we'll hold on this one. Down to C. Boron only has 3, and boron is special. It only wants to have 6 in its valence shell. That's part of the size of the atom, its valence shell, and also the fact that it does have 3 unpaired electrons. It can just pair those and then be happy. So we have 3 from the boron, And then we have 3 times 7 for the fluorines. So that's going to equal 24. So let's count up and see if we have the right number. So 2, 4, 6 for the bonds. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that guy's good. Okay, oxygen is pretty easy. Oxygen has 6, and then there's 3 of them. So we need to find 18 valence electrons. So, and I'm sorry I'm going to rush through this, but I think you get the point at this point. So, sorry, bad word choice. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So that's enough electrons, and that's correct. So let's look at this guy last. 5 for the nitrogen plus 3 times the H. Each have 1. So that's going to equal 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that's good. So the B, choice B was the only one that was wrong. So that means that that is the correct answer. All right, number 13. So this asks which molecule has 1 pair of non-bonding electrons on the central atom. So the easiest way to do this is just to draw all of these out. So fortunately, we already saw some of these. So we already saw CO2 from the first problem. And we're looking for 1 lone pair on the central atom. And we can see that that is not the case. So the answer is not B. So we also saw BF3 on the last problem. So BF3 was right here, and that structure does not have any non-bonding electrons on the central atom, so that one is also wrong. So SF2, I think we did that one also, or something very similar. Okay, we did OF2. So OF2 we saw looks like this. And we talked earlier about how with Lewis structures, you can kind of, oxygen is going to act in a similar way to sulfur because they're both in the same family, so they both have 6 valence electrons. So we can redraw that with an S in the middle instead of an O to get SF2. And this guy has 2 pairs of non-bonding electrons. So that one's out as well. So next we'll look at PCl3. So phosphorus is similar to nitrogen. It's right below it on the periodic table. So we've got 5 valence electrons. And then chlorine has 7. And then there's 3 of them. So we're going to end up with a total of 26 valence electrons. And we'll put the P in the middle. So halogens are also always terminal because they only want 1 more electron, so they only want to bond once. So chlorine, fluorine, iodine, all those only want to bond once. Also bromine, can't forget about bromine. And we're supposed to do 26 valence electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So our last two have to go on the phosphorus. And then let's check to see if we should make any double bonds. I kind of already said halogens don't form double bonds because they only want one more. So these guys have to go on the phosphorus. So that one's looking like a good answer choice. So let's just make sure that it can't be SO3. So SO3, S is different than the oxygen, so that's why we're going to put it in the middle. And then also, it is less electronegative than oxygen. And we'll have 6 for sulfur and 6 for oxygen. So we're going to have 24 valence electrons. Didn't leave myself too much space. But 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And what we're going to do here is, like I mentioned before with sulfur, sulfur can have 6, excuse me, not 6. It can have more than 8 electrons in its valence shell because it's larger and it's in that third or lower row. Because if we were to go through and look at the formal charges of SO3, we would see that we would be getting a lot of positives on the sulfur and negatives on the oxygen. Because if we look at the formal charge, oxygen has 6 valence electrons, and then right here it has 1, 2, 3, 4, 5, 6 for the lone pairs, and then 1 for this single bond, so 7. So it's going to equal -1, so this would have a -1 charge. These two are identical. And then this sulfur, you'll notice that this was not a charged compound, so the minuses have to equal the pluses. And we also notice that 6 valence electrons minus 1, 2, 3 single bonds. Oh, sorry. It's going to be +3. So now we're going to end up with a +3 on the middle, which is extremely unfavorable. So how that's going to work is all of these oxygens are going to share with the sulfur, and we're going to end up with double bonds. And then that makes this answer choice wrong because we don't have one pair of non-bonding electrons. So the answer by default has to be A. And now we're ready for our last problem. So let's look at the Lewis structure for NO3. So nitrogen, 5 valence electrons, oxygen has 6. Alright, and we have 3 oxygens. So we've got 23, and then this has a minus on it. So that means that we have to add another electron. So we have 24 valence electrons that we can work with. So nitrogen goes in the middle, 5 valence electrons, lower than oxygen, which has 6. And then let's put 24 on here. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So this nitrogen, we can see only has 6. So we want at least one of these oxygens to be sharing with the nitrogen. So what we'll do is we'll say that this guy is sharing here. And we'll redraw it. And then we'll count up some formal charges. So we know that this entire thing has to have a -1 charge because of the NO3 minus. And then let's count the formal charges. So we'll start with the nitrogen in the middle. And that's a colon, not a dash, to not confuse with minus signs. And then we'll do oxygen number 1, oxygen number 2, and oxygen number 3. So, and we'll say that's 1, 2, and 3. So for the nitrogen, it has 5 valence electrons, and then here we count the single bonds as 1, so 1, 2, 3, 4. So -4 means that the nitrogen has a +1 charge. So we'll put a plus right here on this nitrogen. And then oxygen number 1 has 1, 2, 3, 4, 5, 6, 7. So we've got 6 valence electrons minus 7 from the number we counted, and that's going to equal -1. So this oxygen has a negative on it. So this oxygen number 2 is the same because we have 6 valence electrons minus 7 that are associated, because see, these guys are the same. 3 lone pairs, 1 single bond. It's also a -1. And then this last oxygen is going to have 1, 2, 3, 4, 5, 6. So 6 valence minus 6 that we counted is equal to 0. So this guy is going to have no charge on it. So this is going to be our best Lewis structure because we can't make this guy share with this nitrogen, because that would give it a +2 charge on the nitrogen, even though this wouldn't be charged. And what we want is, we want to get rid of charges ideally, but if you can't, you don't want one atom to have like a +2 or a -2. That's much more unfavorable than just having many -1s or +1s. So this is the best structure that we're going to come up with. So let's look at the question here. It asks how many single bonds, how many double bonds, and how many lone pairs. So we have 2 single bonds and 1 double bond. And then let's count up our lone pairs. So we have 1, 2, 3, 4, 5, 6, 7, 8. So do we have one that's 2, 1, 8? Yeah, answer choice C. So that one is correct. All right, so that was all 14 problems from the PARTE session, and hopefully that was helpful. If you have any questions, feel free to post something on Piazza, and we'll try to get back to you as fast as possible. So, see you guys.